The topic of today's webinar is improving PHEV thermal management by integrating high-fidelity powertrain model and a high-fidelity thermal simulation model. My name is Sudhi Upalluri. I'm the Technical Director at Computational Sciences Experts Group, and I am joined by Doug Kolak, who's the Business Development Manager at Mentor Graphics. So before we jump into integration of powertrain and thermal model, we ask ourselves, why should we care? In fact, we said, why should we be integrating these tools? And I'm sure you're asking yourself the same question. Why should I care about this topic? You should care about this topic because PHEVs and EVs have changed the thermal management game. So what you're looking at is the power consumption of an EV. And the blue line shows the power consumption when the heating and cooling are off. So it's just plain driving in a UDDS drive cycle. And then the red and the green lines are with the power consumption with the cooling and heating on. And as you can see in an EV, the power consumption with the heating on is more than 3 times the power consumed when the vehicle is driving. So essentially, there's more power being consumed for heating than to just move the vehicle. So it's more like heater on wheels rather than a car with some heating. So in PHEVs and EVs, thermal management is not just a heat that needs to be managed. In conventional vehicle, they used to say that thermal management is the heat that needs to be managed. In fact, if you did a great job with thermal management, then people won't even know you're there. So as long as people don't even know you're there, you've done a fantastic job. That's not the case with PHEV and EVs because their impact is quite big on MPG and battery range. You're squarely in the middle of all the design. And thermal management is not just about how much power it's consuming. In fact, in plug-in hybrids, it also matters whether the engine will turn on or not, and what the drivability of the vehicle looks like based on the thermal management. So, as an example, here is some data from a plug-in hybrid. And what we are showing in this graph here is the black line is the coolant temperature. So this is cold CO drive cycle. So this is FTP drive cycle with 20F ambient. And so the black line is the coolant temperature. You can see the coolant temperature starting at 0 degrees. And it's warming up. And until the coolant temperature reaches a target temperature, in this case was about 65 degrees here, the engine keeps running on. So the purple line shows the engine speed. So you can see that the engine keeps running until the coolant temperature reaches 65. And once it gets to 65, the engine turns off. And then the coolant starts dropping. And the coolant temperature is dropping because the cabin heater is on and it's drawing heat out of the coolant. And then when the coolant reaches a minimum flag here, which is about 50 degrees C, the engine comes right back on again. So basically, the engine is coming on and off purely to provide heat. And so our thermal management strategy and controls not only determine the cabin heating, but also whether the engine will run or not, which is a big impact on the MPG. And our analysis of these controls of many plug-in hybrids and electric vehicles show that OEMs are still figuring this out. We find that many production vehicles have a lot of low-hanging fruit on the table, and their thermal management strategy could be improved quite a bit. So there's a lot of opportunity for it to be smart energy management, is how we would like to call it, because at this point, all of the energy is electrical. To drive is electrical, heating is electrical, and AC systems are electrical. So why integrate powertrain and thermal systems, you might ask? We are today doing 1D modeling of conventional vehicles and 1D tools. And with plug-in hybrids, our models will become more complex and we will continue to manage it that way. Why integrate the powertrain model, you might ask? And here is an example thermal system network of a plug-in hybrid. As you can see, the plug-in hybrid thermal system has complexity of a conventional vehicle and an electric vehicle plus more all combined together. So the light blue line is the engine cooling circuit. Again, it is a little bit simplified here, but you can see the engine structure, you can see the EGR, you can see the EOC, cabin heater, radiator, all of those in there. In addition to the high temp circuit, you have the green, which is the transmission, the purple all the way in the bottom, which is the low temp circuit with the power inverter module, motors, and charging. And then you have the battery circuit, which in turn is connected with a cooling circuit. And with all of this complex thermal network, there are a number of components that need boundary conditions that come in from a powertrain model. So you would need the engine speed to run the coolant pump. So the engine speed determines the coolant pump speed. You need the engine heat rejection, which determines, well, what's the main heat source in the high temp circuit. In addition to that, you have the vehicle speed, which determines the ram airflow coming into the vehicle. And you would need exhaust mass flow and temperature if you have EGR cooler or exhaust heat recovery device. These are just some examples. Of course, you need motor heats, you need battery heat load, you need transmission heat loads and transmission warm-ups. So there's a lot of different boundary conditions that you would need coming in from a powertrain model. So the thermal model is actually not independent of the powertrain model. And so let's look at the powertrain model. And I'm going to simplify here into a conventional just to keep the point simple. A powertrain model cannot just be run with a drive cycle. Yes, it's a key input that goes into the model, and you have a lot of component details in here for the engine, the transmission, the shift maps, the efficiency curves, and all of that. But you also need the engine warm-up in the powertrain model, because the engine warm-up determines a number of fuel consumption parameters in the engine that we will look at. You will need the axle warm-up. The efficiency of the axle is closely tied in with the axle warm-up temperature. You would need the transmission warm-up temperature, which, just like the axle, affects the efficiency of the transmission. And the electrical and mechanical accessories on the engine are a function of the temperature of the warm-ups and come from the thermal model. So if you have your fan power consumption, your coolant power consumption, your PTC and compressor power consumption, all come in from a thermal model and need to be fed into the powertrain model. Essentially, the answers from the thermal model feed into the powertrain model, and the answers from the powertrain model feed into the thermal model. So the coolant temperature, the oil temperature, the transmission temperatures that you calculate, the fan and coolant pump power that the thermal model will calculate, go into the thermal model, and the thermal model will calculate the updated engine friction, the updated transmission and final drive efficiency, the updated electrical and mechanical accessory load based on the fan and coolant pump power that it's consuming. And then it would calculate the vehicle's behavior, and in case of hybrids, it'll calculate whether the engine needs to be on or not. And then that data gets fed back into the thermal model, which in turn are really the boundary conditions into our thermal model. So essentially, the answers between the two are quite interdependent. Let's look at the two different tools that we used for integration and doing an analysis. The two tools that we used are Powertrain Live and SimCenter FlowMaster. Powertrain Live is a vehicle level modeling software. It's a high fidelity, forward-looking vehicle simulation software, and I'll talk about a couple reasons why we picked Powertrain Live and reasons why we picked FlowMaster. Powertrain Live, one of the primary reasons we picked Powertrain Live is the built-in correlated models for analysis. So as thermal management engineers, we don't really have easy access to the vehicle data. Even if you're an OEM, you don't have access to a full vehicle data to build your own powertrain model. Many times they are in a certain group and you don't get the answers very easily. Or even if you get all of the information, just suppose you're a smaller OEM where all the information is really easily shared, you are a thermal management engineer. You do not want to be spending 4 to 6 months developing and correlating a vehicle model. Powertrain Live has quick start vehicle models. So if you're working on conventional powertrains, we have some standard vehicle models which are correlated to chassis dyno data. So there is a Ford F-150 vehicle model in here. There is a Dodge Ram truck vehicle model, certain sedans. For hybrid powertrain, we have a Toyota Prius hybrid vehicle model. Plug-in hybrids, there's a Chevy Volt. Electric vehicles, there's the Ford Focus EV, VW e-Golf. So there's a number of representative vehicles for all different types of powertrains readily available. And these data is correlated to chassis dyno data, which makes it easy for a thermal management engineer to pick up and use it for thermal management studies. And one of the second reasons why we picked Powertrain Live was the thermal parameters are readily available in Powertrain Live. So in the engine heat rejection is calculated. Calculation of engine heat rejection is not very straightforward, but there are correlations inside Powertrain Live that allow it to calculate engine heat rejection in the drive cycle given the operation of the vehicle. Same thing with exhaust mass flow and temperature. Exhaust mass flow might be straightforward, but exhaust temperature, there's proprietary algorithms that allow it to calculate estimated exhaust temperature. It also calculates transmission heat rejection, axle heat rejection based on the efficiencies. So there are a number of thermal parameters that are readily available in the powertrain model that allow a thermal engineer to take these parameters and integrate it into a thermal model. So here's an example of exhaust mass flow and exhaust temperature traces that are available for a given drive cycle. I've included a brief video on Powertrain Live just to show you what type of inputs are available in the model and what type of outputs are available for those of you who are not familiar with Powertrain Live. As you can see, that Powertrain Live is a web-based software as a service. So you don't have to install and worry about pulling the whole powertrain together. This is like having a mule vehicle readily available. And there are a number of different vehicles of conventional and plug-in hybrids that are available. And so let's look at what a typical Chevy Volt vehicle inputs and outputs look like. In the interface, as you can see, there is all the different subsystems on the left. And we're looking at the inputs for the chassis. So on the left, you can see the battery subsystem, the engine, the motor subsystem, the controls, transmission, wheel, driver, so all of the necessary subsystems that you would want to change the inputs in and get parameters for. These are the inputs for the engine subsystem. And as you can see, the standard numbers are on the left and all of the maps are on the right for input. Here's an example. Let's take a look at the fuel consumption map. And you can see all of the maps, all of the tables are interactive, so you can see what they look like. And you can change these numbers at a click of a button, and I'll show you that in a second. Let's look at the battery subsystem. The battery subsystem, again, has the number of cells in parallel and series. And on the right has the RC circuit representation and their values. So basically the resistance as a function of state of charge and battery temperature, the capacitance, all of those can be input in there. Let's look at the motor subsystem, for example. Here are the efficiencies maps based on speed and torque of the motor, and here's the PEM efficiency. So essentially all the critical inputs for the subsystems are already in there. Here's the driver subsystem, and this is where you would put in the drive cycle. So we're showing you how you can copy and paste any drive cycle in here. We have some standard drive cycles that you can put in here. We're showing you a highway FET drive cycle, and you can copy paste your own drive cycle in there. For our scenario, we're looking at a UDDS drive cycle, and I happen to have this drive cycle handy, so let's click on the UDDS drive cycle and pull that drive cycle up. And so here is the UDDS drive cycle. And you can see the run simulation button up at the top where you can click run simulation and get the answers very, very quickly. So here are some of the key thermal parameters that you can look at. So we're looking at, for the battery, for example, the current versus time, but also the bottom graph, battery heat rejection versus time. And this is one of our key boundary conditions as we are running a thermal management model for a plug-in hybrid. So let's look at motor. This is the other key parameters that we would use for hybrid co-simulation. We have the motor heat rejection versus time at the bottom that we can use as a boundary condition into the thermal model. And in addition to that, you can see the overall vehicle cycle fuel economy. So if you look at the numbers up at the top, they're all displayed for the drive cycle, what the cycle average fuel economy is, what the overall CO2 emitted is. In this, the model was running in a pure EV mode, so there's no fuel consumed, but you can see how much battery was consumed here, 1.35 kilowatt hour for the drive cycle. And so this allows you to, when integrating with the thermal model, be able to quickly understand any thermal changes you make. You can see what is the impact at the vehicle level and what does it mean. All right, let's move on to the other tool, Flowmaster. I think many of you are already familiar with the Flowmaster tool. A lot of the OEMs use this as a standard tool for doing cooling system models. One of the reasons why we picked the cooling system model was this built-in standard models in Flowmaster. So when you open up Flowmaster, you have some standard models available. And this is very analogous to what I was saying about Powertrain Live having standard models available. So as a thermal engineer, when you are tasked with evaluating a certain technology, you're not staring at a blank page when it comes to a vehicle model. You would have a representative vehicle model, and you're not staring at a blank page when it comes to a thermal system model. You would have a base thermal system model onto which you can do A to B comparison studies for your technology. All right, so let's talk about the mechanism of integration, how we integrate the Powertrain Live vehicle model into a Flowmaster thermal model. And the integration is done using controllers and gauges. All of the variables going into the thermal model go in through the controllers. So the variables that are going into the thermal model are the engine heat rejection, engine speed, which is determining the coolant pump speed, vehicle speed, exhaust mass flow and temperature, motor heat rejection, which goes in as an input into the low temp circuit, and battery heat rejection, which goes into the battery loop. And all of these boundary conditions go in through this controller, and we have coded in a way where at every time step, the value from powertrain model is brought into the thermal model using the controllers. So these are the incoming variables from the powertrain. The gauges are the components that take the value from the thermal model to the powertrain. So for example, this gauge here takes the pump power and sends it to the powertrain model as a parasitic loss, as an accessory load. This gauge here reads the oil temperature and sends it to the Powertrain Live, and this happens at every time step. In this analysis is 1 second. And so the 4 gauges that we have set up in our example here is the coolant temperature is being sent to the powertrain model, and then the fan power, pump power, and PTC power are being sent in. And we're looking at a cold ambient warm-up condition. So here is the interface for the integration of Powertrain Live with a 1D thermal model, the first example being Flowmaster. So you can see all of the different variables from Powertrain Live that can go into a 1D thermal model, and we can, for now, have the way we have set up all the variables coming into the powertrain model. So this is coming into powertrain, and these are the variables that are going out from the powertrain into the thermal model. And this interface allows you to set up what the network names are and which variables you want to send them in. All right, let's look at an example simulation with this integrated approach for a plug-in hybrid. And what we're trying to see is for a production plug-in hybrid. So we were looking at a 2016 Chevy Volt. We wanted to see what is the impact of an exhaust heat recovery heat exchanger and how much does it impact. And I'll show you the methodology here. So on the top left is the schematic that was provided by the OEM. We pulled it out of the manual. Again, we recognize that this is highly simplistic. The actual cooling system is quite complex, a lot more bends, a lot more heat exchangers in there, the EGR coolers in there. But this is a simplified cooling system which actually is good enough and serves the purpose that we are looking at for predicting a baseline coolant warm-up. And so on the right is the corresponding translated 1D simplified thermal model of the same schematic. And so you can see these yellow boxes that we have in here. These are the controllers where the variables are coming in from powertrain. So this is where the combustion heat would come in. This is where we have the coolant pump speed come in, etc. And these are the gauges here now in circle where the coolant temperature from here goes out and pump power from here goes out. So pump power from here over here goes out from there. So essentially we have a simplified 1D model. And after we got all the boundary conditions from the vehicle model and have adjusted and verified a few parameters, we find in the bottom left the correlation to be very good. So the blue line shows the test data from the chassis dyno for a UDDS drive cycle, what the warm-up looks like. And this is a charge depleting mode. And the orange line shows the warm-up of the thermal model that we predicted with the boundary conditions coming in from the powertrain model. And we find that we match the warm-up profile, the decay, the heat draw, and then also the engine start and stop within a pretty acceptable accuracy. So this is the base thermal model. Our base vehicle model was for the Chevy Volt. And so this is showing the boundary parameters calculated by powertrain life for the Chevy Volt. So you can see the engine speed at the top left. So this is a charge sustaining mode. So you can see the engine speed at the top left, which gets fed into the thermal model. You can see the engine heat rejection being calculated. These are just some of the parameters that are being calculated and being sent into the thermal model. Here is for charge sustaining. We'd see that the blue line is the warm-up of the coolant, and this is the coolant profile. So this is the baseline coolant profile warm-up. And you can see that until the temperature hits this target temperature here, you can see that the engine remains on all the time. So as an example, here is where the vehicle is stopped. And we expect that the engine to turn off, but the engine remains on, as you can notice here, until the target temperature is reached. So this is, again, the impact of the thermal management system on the fuel consumption and on the powertrain and the engine being on. So what we wanted to study was the impact of the EHR heat exchanger. So we went into our correlated model, and we put in an exhaust heat exchanger upstream of the heater core. The boundary conditions for exhaust mass flow and temperature came in from the powertrain, and this additional heat was added into the thermal model. So let's look at what the thermal model's warm-up prediction is. So the blue line was our baseline. The faster warm-up is from the orange line. And what you'd see is that our target temperature of 65 is hit earlier over here. So if you remember, the engine remains on at least until this temperature, no matter what, because the coolant needs to hit the target temperature. And now our target temperature is hit sooner. And that means that we have almost 50 seconds or so worth of engine on that can be reduced because our engine is warmed up faster in this case. For proprietary reasons, we've refrained from quantifying how much exact fuel consumption this is and what this really means, but we at least wanted to show that as the warm-up is changing for the vehicle, you can see how it impacts the engine on time and potentially significant amount of fuel consumption for that drive cycle. So from this webinar, I wanted you to have at least 3 takeaways. The first takeaway is for plug-in hybrids and EVs, we no longer have a conventional, it's just that heat that needs to be managed approach for thermal management. The power consumption of thermal management is large enough to make a pretty big impact. Many cases, especially EVs, the power consumption can exceed and does exceed the driving energy required for the vehicle. And this is not an optimized system or easily optimizable system, by the way. Many vehicles that are out in production are still figuring out the smartest way to do energy management. And the only way for a thermal engineer to figure out a smart strategy is to integrate it with the powertrain model. Not only because you need the boundary conditions from it, but the operation of the powertrain, the engine turning on and off, the variables, the heat rejections and the exhaust mass flow change and are dependent on how the thermal system is operating. And in the third takeaway, the case study that we saw shows that if you, as an example, take an exhaust heat recovery heat exchanger and you put it in a plug-in hybrid, the impact is a little not intuitive. One would expect, it heats up the coolant faster, so perhaps it has lower friction and lower fuel consumption. That might be true, but that's only part of the benefit. One of the bigger benefits is that the engine can be turned off earlier if the thermal system meets its target temperatures faster, and it has an impact on engine on-off. And not only just that, but then also the drivability and the NVH of the vehicle. With that, I would be happy to take questions.